All right. So on 1.127, we're asked to straighten out how many corners does a cube have in 4 dimensions? How many faces and how many edges? Okay. Let's see if we can straighten maybe corners first. Corners seem like a good choice. All right, so first things first, I think I probably need an analogy. Let me have a couple lower dimensional analogies. What does kind of a cube in 2 dimensions look like? First, what's a 2-dimensional word for a cube?
Square.
Good. Yeah, square. Okay, so and I'm assuming they're kind of talking about the unit square or the unit cube. Does it really matter?
No, it'll have the same amount of corners and edges and faces.
Yeah, it doesn't really matter how you count this. So I'm going to assume it's the unit cube to make my brain a little bit more capable of handling this. So where is this first corner?
Zero, zero.
Yeah. I'm going to put that one at the origin. Where are the other 3 corners of the unit square?
0, 1, 1, 0, 1, 1.
0, 1, 1, 0, and 1, 1. Perfect. You guys with me on that? Okay. So the way that I kind of think about the corner, well, maybe let me think in 3D next. Okay, so in 3D, I'm still going to have the origin, 0, 0, 0, as a corner. What are the other corners?
One, 1, 0.
Okay, 1, 1, 0 is out here.
0, 1, 1.
0, 1, 1 is up here.
And 1, 1, 1.
And then yeah, up here is 1, 1, 1.
And then all the ones we had on the 2D square.
Plus 0, 0, 1.
Yeah,
0, 0,
so
1, 1, 0, 0, 0, 1, 0.
okay, hang on. I gotta let's see. So 0, 0, 1 be this guy, right? Oh, whoops, that's not the right one. That's not how axes work. How about 1, 0, 0? And then back here we've got. You guys see why this is getting kind of weird? 0, 1, 0. It's basically just a lot of numbers to keep track of, right? But what's going to be the common theme with all these points? So these points look like something and something, right? And what's common between these numbers? Like what can they be on the 2-dimensional square?
Either 0 or 1.
Yeah, they have to be either 0 or 1 in either case. You guys see that? In my next case, the cube, right? I have kind of 3 spots to fill in. and my picture got hella messy, but they are either 0 or 1. And I actually really like what Cody said about, yeah, it's basically this square and then another copy of the square, and then you connect them with lines. You guys all feel that? So if I was thinking about how to draw a cube, right? I've got a square and the dotted square in the back, and I'm connecting them with lines. Now, personally, I tend to draw the kind of the one on the bottom and the one on the top, and then connect them with vertical lines, right? So I tend to do this. There's a bottom square. Here's a top square, connect, 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 connect. You guys all with me on that process? So if I thought about that, I would think, all right, so like this is the square. I'm gonna call the square S. So down here, I have like S and 0. And up here, I have like S and 1. You guys see that? Okay, so how many edges or how many corners do I expect my 4-dimensional cube to have? I can't really draw a friggin' picture of it, right?
16?
Yeah, I think I expect to have 16. One way I could see that is I could think, okay, well, it's a tuple, right? It's a point in 4 space, and all of these are filled with either 0s or 1s, and all of them are valid. You guys see that? If I think back to here, there were 2 options for this first spot, 2 options for the second. That's 2 corners. Wait, not 2 corners. Counting's hard, Joe. It's 2 times 2 corners. In the 3-dimensional space, it's 2 times 2 times 2 corners. You guys see that? That's really that the corners are the old corners with 0 at the end, or the old corners with 1 at the end. You guys on board for that guy? All right, so I think this one's going to be 16 because it's 2 times 2 times 2 times 2 corners. If we had to make a conjecture for n space, what would it be?
Two raised to the n.
Yep, exactly. Really, that's that a point in n space has n slots, right? And then I'm going to fill them all in with either a 0 or 1. So I have 2 choices in each spot. You guys with me on that? Okay. Now, the next things are going to get a little harder. Because this is where we have to think a little bit harder. All right, so let me think here about going from squares to cubes. When I put a square at the bottom and a square at the top, I'm wondering, yeah, let me see how to say this. Trying to make an analogy here, and I don't want to screw up your brains too much. Let's screw up your brains a little bit. All right, what are the faces of the square?
There's one.
Yeah. Okay. Let me.
Are they lines?
Yeah, I would say the faces of the square are the lines. That's going to make the best sense with the analogy they're asking here, how many three-dimensional faces there are. So that's one minus, that's like the facets that are one lower dimension, right? Does that kind of make sense? In this case, the faces are the edges, which is a little weird. There's better verbiage for this higher in math when you do more geometry. But for right now, we're just kind of playing combinatorics a little bit, right? All right. So I think that we had here kind of initially, we have 4 edges. That seems obvious. The edges are the kind of one-dimensional faces, right? And then we also have 4 faces. In the case of the square, things are a little confusing because the edges are the faces. In this cube, I have how many edges and how many faces. What have I got in the cube? How many faces does a cube have?
6.
Yeah, it's got 6. You guys see that? How many edges does it have?
I think 12.
Yeah, it seems like it's got 12. Okay, so let's count those 12. How'd you count them, Grayson?
With my fingies.
With your thinkies?
Yeah.
Yeah, if I was to count them, I would say that the number of edges, right, are 1, 2, 3, 4 from the square with 0 attached. 4 more from the square with 1 attached. Right? And then 4 more to attach those 2 squares. You guys see that? So if I had to count the edges, I'd say it's twice the number of edges from the square plus the number of vertices, corners, sorry, of the square. You guys all see that? Did I lose you guys? A little bit.
I've got it, I think.
So I'm thinking that the way you make a cube is you take a square and then you lift it and stop at some point, right? And then all this lifting, the corners traced edges as they went, and you still had edges from the bottom and edges from the top. So that's where I got my 12. So if I had to guess about the 4-dimensional thing, I would think, okay, it should be twice the number of edges from the dimension down. And so I'm thinking about a cube, and I'm kind of lifting a cube through that 4th dimension. Right? And I'm going to have the edges that I had from the cube at the bottom and the edges I have from the cube at the top. So I think that's going to be, how many edges did the cube have at the bottom?
$12.
Yeah, it had 12. So I think we're going to have 2 times 12 plus. And then I need the number of corners. How many corners did it have?
6.
Wait, what?
Sorry, not 6.
Not 6.
16.
8. I mean,
8. There we go. So I think it's going to have 2 times 12 plus 8. And if you're really, really careful, you can actually find this out. So if you draw yourself a cube, and then very carefully select it, copy it, paste it, word pen properties. Turn it a different color. Turn your pen a different color. And now I need to connect all the edges. You guys see that? So I need to connect this edge here to it, or this corner here to its corresponding corner back there. You guys see how this is going to be a pain in the ass to do? It's actually a lot easier if you do this thing. And then draw them this way.
So that's why I always see that depiction of a 4-dimensional cube. I see.
Yeah, you've probably seen this thing some places. It's called a Tesseract. This drawing of it. There's another drawing. What's that?
Whenever I've seen that, I've always thought of it like adding as time. So there's a cube and then it grows out into like a bigger cube and then you just connect.
Yeah, that's perfect.
That's kind of how I've thought about it.
Yeah, that's totally legit.
And
You can.
I think of it as 4-dimensional space. So as you travel through 4-dimensional space, since we can't see 4-dimensional space, I'm getting into it way too much here, but since you can't see 4-dimensional space as you travel through it, we're just seeing the 3-dimensional parts of 4-dimensional space. So that's why it looks like it's growing as a cube.
Mm-hmm. Yeah. Yeah, that's what Jordan said.
But instead of time, it's 4-dimensional space is all I wanted to change.
It's
Yeah, I know.
kinda-
I'm just teasing you.
It's
That's
kind of like
space
if
is
you
time.
treated the equation of a sphere and the radius as its 4th variable. So that like as the radius grows, that's its 4th variable. You know, like
Yeah, that's another way you can kind of think of these things. So does everybody believe me now about the edges? Yeah. So the 2 times 12 is the green edges and the blue edges, right? And then the pink ones are the 8. You guys see that? And then we could actually use this picture to count the faces. It's a little bit boring because it's only, well, it's 2 times the number of faces that it had in the previous dimension.
why is it 2 times? Because when you went from a square to a cube, it was just plus 2 faces.
Oh, sorry. Maybe we should actually count. Let's see. So it is the, yeah, we should definitely actually count. Uh-oh, I lied to you just now. Sorry, that happens. Let's see. So we have, oh, I forgot to draw one. You guys see that? There's only 7 pink edges in here. Which one did I forget to draw?
The one coming like at us in the POV.
Yeah, that one. that one. I don't know why it keeps going underneath that thing. Sorry, I'm crappy at my job. I'm a hack and a fraud. Okay, so we could count them. Let's see. So there's one kind of pointed at us. One to the. See, so it should have been. Oh, yeah, I lied. I lied completely. So let's think about the from the square to the cube, right? We took the edges. So a new face, right, is an edge and these guys. Right, so a new face is the image of an old face. Plus the one on the bottom and the one on the top. So it's probably twice the number of edges plus 2. Is buying that?
I don't see how it still behaves with the transformation between square and cube.
Yeah, that's fair. Okay, so another way we could probably get at this is we could figure out how many edges you need to bind a 3-dimensional face. You guys see that? So in this analogy, right, I could think about the number of faces. Each of them is bound by edges. The trouble that I'm having is that a 3-dimensional face is going to be bound by 2-dimensional sides. So I'm sure I have edges, right? Faces. So if I was doing this on kind of the picture, right? If I want to count the number of 3-dimensional faces, I'm going to think the outside of the whole thing is a 3-dimensional face. The inside of the whole thing is a 3-dimensional face. You guys with me on those? Okay, so I think I'm going to have kind of the, let's see, I guess I should call them green and blue. I'm writing something else. So I think I have the green face, the blue face, and then I have this one. So that thing that I've so far encircled, what dimensionality is that?
2.
Yeah, that's 2-dimensional, right? So that is one of the faces, one of the sides of this 3-dimensional face I'm trying to find. You guys see that? So it's one side of the green thing. You guys all agree with that? If I trace the rest of the green faces out, I'd have one of the 3-dimensional faces. You guys on board with that?
So for a cube, if we were saying a 3-dimensional cube and it asked for how many 2D faces, there's 6?
Yeah, exactly. Right, because I'd pick
Okay.
a corner and then I'd trace out 1-dimensional things until I got around a 2-dimensional space. You guys see that? So I'm trying to find the image of a cube in here, right? Something that looks like a cube. It's kind of mashed because of my perspective, right? Because I can't draw because frankly, I'm trying to render a 4-dimensional object on a 2-dimensional object. It's a little bit fraught with difficulty, right? So if I'm going to count this thing up, I need to find the other 2-dimensional faces that are attached to this green one. So this is one here. You guys see that? That's the sort of left half of looking through green at blue. You guys on board with that one? Okay. Then I have connected to that one, this blue face. You guys on board with that guy? Okay, now how about this dude? That's got a pink edge, a blue edge, a pink edge, and a green edge. That's kind of the top of looking through the front of green at blue. You guys see that? So I've picked out 3 of the sides of this thing. Another one is here. That's the kind of bottom of looking through the front of green at blue. And then I've got the right-hand side. You guys see that? Okay, now, how many ways are there to look through green at blue? I kind of-
6.
Good. There's 6, right? The faces of the old cube. So I've got green and blue and 6 more. Right, so it's the number of old faces plus 2. Which kind of makes sense, right? So here's the number of old faces, right? Like this guy, this guy, this guy, that guy. Each of those gets smeared up. So each of those old faces makes a new face. And then there's a top and a bottom. So in this case, there's like a beginning and an end, right? A green and a blue. Those are kind of playing the roles of top and bottom. And then there's the other 6 that are made by the edges being smeared through time. Or, sorry, the faces being smeared through time. Those are two-dimensional, getting smeared through time, making it three-dimensional. You guys with me on that? Does fully twist all your heads off? The answer was 8.
I counted 24 faces.
Okay, so what do you mean by a face? So they're asking for 3D faces.
Oh, how many 3D faces? Oh, okay. I wasn't going.
Now this is actually an interesting question. So we've got 16 corners, right? So if I wanted to summarize my information about my 4 cube, I have 16 corners. I have 24 plus 8 is 32 edges. And then my claim is I have 8 faces. And this is why I'm kind of whining about having to use these words. Faces is a dumb word. You guys see that? Because between corners, edges, and faces, when the book says 3D faces, they skipped a dimension. You guys see that? Grayson's saying there's, how many did you get?
24.
24. Does that seem right? 6 plus 6 plus twice 6. Yeah. So there are 24 of something, but I don't have a word for it. Those are kind of 2D faces. You guys see this?
Yeah.
Okay. So if you wanted better vocabulary, these are the 0D things, right? The corners. Those are the points. How many dimensions do edges have? Yeah, edges are 1-dimensional. These are 2-dimensional, and these are 3-dimensional, right? So mathematicians being lazy just call them all the same thing, but with the number attached. So There are 16 zero simplexes. There are 32 one simplici. There are 24 two simplexes and 8 three simplexes. And I said one simplici. I should have said one simplexes. That's simplex. It just means whatever the hell that analogy is in this dimension. You guys got that?
Yeah.
And it's really to avoid this confusion about faces and faces when you get to 3D or 4D. All right. Are you all colored confused by that? Or was that mostly clear? It's okay to be pretty confused by this thing. I really wish we were in person because I have one of these sitting on my desk and it helps to play with one. Make one out of pipe cleaners or something and then count the pieces. It's actually really, really cool.
Marshmallows and toothpicks.
Oh yeah, that's disgusting. Make it out of marshmallows and toothpicks, and then after you're done with it, microwave it. Okay. Let's see. So 28 and 29. Okay, good. 28 and 29 are going to lead us into our kind of next section anyways. Okay, 1.1. Oh, wait, I'm going to stop this. Any other questions about that?